Recording in progress.
So my clock says 8. I mean, what do you think? Shall we give it more? Or?
Yeah, we can. I don't know. Sebastian is the boss today.
Okay, good. Okay, I shut up. It's a good point.
Just maybe 1 or 2 minutes in case more people are joining, and then we will start. Okay, so I suggest we start the session. So hello everyone. So today we start with the first session with 3 talks related to different laser facilities around the world. The first presentation is from Marco Galimberti from the Central Laser Facility in the UK, and he will talk about new high power laser facilities at CLF. So please go ahead. You should be able to share your slide.
Sure. Okay. Well. Okay. Good morning. I'm opening this morning. So, I'm presenting here the 2 major projects are ongoing at the CLF at the Rutherford Laboratory. So in particular, the 2 projects, one is the EPAC, is the Stereo Photonic Application Center. And the other one is a Vulcan 2020 essay proposal. I'll explain a bit later, and then a few conclusions. So the Stereo Photonic Application Center, we call it just EPAC for simplicity, is a new center, a new building that has been funded, £88 million project. And the aim is to provide the 1 petawatt laser at 10 Hz mainly for electron acceleration and X-ray, but also with fundamental research. And is also have a backup as backing from the industry. So the idea is not only to do research, but also to provide to the industry possible sources for proof of principle test. And is the major investment of the UK in the plasma acceleration. So the building is complete, and we are starting building everything. And we are the first operation is planned to be 2025. So this is a schematic of the facility. Is that in terms of fire as a system with OPCPA front end, is pumped using the dipole 100 laser system that I'll explain a bit later. And the building is bigger than what is needed for this facility. So we have a free space for the future. And that is good. So we can, in principle, in the next phase, adding another laser beam or other capability. So the front end, as I say, is an OPCPA front end, is a dual CPA system to guarantee good contrast. So we have a picosecond OPA pumped by a picosecond conventional laser system, and followed by a nanosecond stretcher, and then a nanosecond OPA to boost energy up to 1 joule. The aim for the front end is deliver at least 100 nanometer bandwidth flat top. The stretcher using transmission gratings to try to keep the contrast as best as possible. Specification is 10 to the 12 at 100 picosecond, but we hope essentially to have the best we can get, really. There is also space for a probe, just a few millijoule up to maybe 100 millijoule to deliver to the target area. And that could be used for optical probe or to switch on a plasma mirror or something like this. The main pump laser is our diode pumped diopole 100 that was developed in-house. And we already have two of those systems in the world operational. One is in Czech Republic in LPHYS', and is working well. And we just finished to install one on XFEL in Hamburg. And the developer is still working because we want to push the limit. We reach under 45 joule in infrared at 10 Hertz. And at the beginning, EPAC, we use one of these as a pump laser. We already have space and the money to build a second one to have more pump energy for the Titanium Sapphire system. But we are very happy with that system because it proved to be quite a reliable system. The Titanium Sapphire amplifier, the main amplifier is Titanium Sapphire. So it's a 4-pass, let's say, normal Titanium Sapphire amplifier. The only thing is to guarantee stability, we have relay imaging for every passes with a chromatic doublet, and the thermal lenses on the head is compensated by moving one of the telescope on the multipass. The head is not cryogenic cooled, but is cooled by helium. So to reduce the thermal load on the head. So the pump, as I say, is pumped by 1 or 2 diode 100, pump from both sides. We're including a pass one-thing compensator because we know that pass one-thing is critical for the electron acceleration, and we don't want to play with the main compressor to compensate angular dispersion. So we have a couple of wedges, and the idea is to use it to compensate dynamically any angular dispersion introduced by the thermal loading or whatever. And obviously, we have a default memo mirror inside the amplifier, inside the Titanium Sapphire amplifier, to have a nice wavefront before the main compressor. Main compressor is a normal 4 gratings compressor. You are using off-plane geometry, similar to Gemini. And the idea is because apparently, well, we know that that geometry has got higher efficiency for the gratings and also require a bit less space. So beam size is 220 millimeter round. And obviously, we're going to have a CW laser to align it without the short pass and so on. The only thing is L shape. We have a folding mirror in the middle, and that was just for the size of the build or the room, really. But also that we need to have a mirror in the middle to be able to rate the first pair of gratings to align. So that will be in hand. The one thing we still need to have some developed to work are the gratings. Because obviously we want to operate at 10 Hertz, and operating at 10 Hertz at that level of energy, we know is a problem on the gratings. So we have 2 options. One is the gold gratings, but we know that the laser will heat up a bit the gratings. And if we are not cooling, it will be not good. So this is why we're developing a gold gratings but cooled. But the other option is go for dielectric gratings that now start to be available. So we are investigating on both options because at the moment we are not confident of either. So this is why we are looking at both. And we still have a bit of time before we actually need the final grating. So this is why we are still working. We are testing some sample for cooling the gratings. And we are also looking for the dielectric. We're doing some tests and damage testing and so on. Actually, they are testing now the dielectric gratings on the second target area of Gemini to see how they last over time, because that is also the other question. In terms of the building, on the ground floor, we have the 3 target area. At the start, we start with the main one. The target area 1 is really long. There is a source area, and there is an application area. So in the source area, where we accelerate electron, and maybe create X-ray or whatever, and there is another area where people can use that source. There is a second target area, is EA2, is for general research. And then there is space for a third small target area, but at the moment is not part of the project. And we have some other auxiliary rooms and labs for preparation. Experimental area 1, as I say, is really long and it's got a long focal length parabola, with the possibility to change the length of the parabola and moving chambers for guarantee the spot is where we want it. So it just be delivered a massive block of concrete for stability that the chamber will sit on it. So is focused on the gas target, and we need to accelerate electron there and create X-ray. That is the early purpose for this target area. Target area 2 is more flexible, can have 3 different focal lengths, and could have a plasma mirror. So that is a more general flexible target area as used in the CLF. That is for, let's say, general experiment, whatever. Obviously, it's not really good for acceleration because it's just shorter. But it's still quite interesting target area, obviously. This is about EPAC. Now, we have another big project, and this is the upgrade of Vulcan laser. Now, this is a long story because the Vulcan, the first proposal was 10 petawatt, was more than 10 years ago, probably 15 years ago. At this time, we put in a request for a major upgrade for Vulcan. It's called Vulcan 2020. And this project has been approved, but is not been announced yet. So this is still a proposal, but we know it's approved. And it's an 80 million project. With this time, we're going to extend the Vulcan building, and it will cost just 20 million. So the rest is, the rest of the budget will be laser and target area. So the main aim for this project is to deliver 20 petawatt, fire one shot every 5 minutes, with long pulses. And with long pulses, the aim is to reach 10 kilojoule, at least 10 kilojoule, aiming for 20. So we're going to have 6 long pulse plus other beams and add other short pulses. I'm going a bit more in detail for it. So the 20 petawatt is based on the 10 petawatt design. So the 10 petawatt was a full OPCPA system and is based on the full, obviously, OPCPA front end. They should deliver 6 joule. About 1 joule. And then we go for 3 stages, OPA stages, the high energy. To deliver, for the 20 petawatt, we need to deliver 600 joule at least before compressor. Ideally, 800 joule to be sure that we are going to compensate every possible losses in the main compressor and on the wind propagation. And we need to have 20 femtosecond as a pass length. Obviously, the pump laser cannot be diode pumped. So we're going to have 2 neodymium glass laser system that need to deliver 2 kilojoule in green, 1 kilojoule per beam, and this to pump the final 2 OPA stages. So, because the user wants higher efficiency rate than Vulcan, so we are developing a gas-cooled disc amplifier. So the aim is to be able to fire 1 shot every 5 minutes, compared to at the moment the Vulcan can fire only a 1 shot every half an hour. So all this laser, apart from the compressor, will be on the 2nd floor on a new extension from the existing building. In addition to the 20 petawatt, the plan is to keep the existing beam made for target area west, and this means 100 joule, 1 picosecond, 100 joule before the compressor, with the possibility to fire 250 joule in 10 picosecond, and reusing the existing beam made compressor. So this one we already have it. Maybe we're going to change the front end. We can reuse the top front end, is a PCPA front end. They will allow us to have a shorter pass and a short pass for that one. In addition, we want to keep the other OPCV Milan we are building. It's called a VOPL. That is a 30 joule, 30 femtosecond. That is a half build. We didn't complete yet, and now we have to relocate it where we are building the new one. But there will be, let's say, a probe for the main 20 petawatt, or as an additional petawatt beam, and need to be synchronized at 20 petawatt. That is another challenging thing. Again, this beam line at the moment was planned to be pumped by existing long pass for Vulcan, but we're going to have another gas cooled disk amplifier, so be able to fire every 5 minutes. All this VOPL is a full OPA system based on LBO. So long pass capability. So in addition to the short pass, we are going to rebuild from scratch all the long passes in Vulcan. And we're going to have 6 20 centimeter long passes. So we aim to deliver at least 10 kilojoule in infrared on this 6 pass beam with, we're going to have shape long pass capability. So that we already have it. So we can shape the long pass, and that will be interested for obviously future-oriented experiment. We are investigating for broadband because at the moment, obviously, we have a narrow band long pass, but the user, they start to ask for a broader band. So we are investigating 3, 2 or 5 nanometer option. All these long passes will be delivered at the same time as the 20 petawatt and the VOPL. So the target area could be pretty busy. In addition, we can reuse the pump laser for the 20 petawatt as a long pass. It can be delivered down to at least 1 target area. And also the 100 terawatt beam can be used in a long pass mode to have another alpha kilojoule. And in this way, we see how much energy we can actually deliver. The aim is to reach 20 kilojoule, but we see what we can do it. It all done also to which the development on the optics we are doing, how much actually the optic can last, really. So all the 20 petawatt laser apart of the compressor will stay on the second floor. So there will be a new pump area is a long laser room where there will be the 2 chain disk amplifier for the pump laser. And then there is a massive amplification area where there will be the two large OPA stages and the final expansion for the 20 petawatt, plus all VOPL, including the compressor. VOPL compressor will stay on the second floor on top of the bunker that is underneath. The VOPL compressor weighs about 20 tons, so it will be interesting to move it up there. The short pass front end will be on the second floor and also with VOPL. They will help for synchronization. So at least we're going to share, the plan is to share the same picosecond OPA between the VOPL and 20 petawatt, and it is a good starting point for the synchronization. There will be a small laser control room on the second floor for sure for the commissioning. We'll see in the future the operation, and a plant room. On the ground floor, we're going to have the existing tap target area. Then we're going to remove everything. There will be a new interaction chamber in the second phase. We're going to have an extension for electron beam dump, for electron beam acceleration. Then we're going to just put an electron beam dump to stop the radiation for it. And then there will be a new target area with a massive bunker where we can deliver all the passes, and a room for the 20 petawatt compressor. So there's a 10 petawatt, the compressor was on the second floor. At this time, we decided to move it downstairs for stability, for a lot of good reasons. There will be 2 small, 2 control rooms for the user, one for the new target area and the other for the existing one, and plant room and the capacitor bank on the ground floor. And with a new entrance, but just with, well, down there, was supposed to be a major entrance, but we squeeze it because we want to use all the space we got for the facility, really. Money detail for the target areas is top, we're going to repopulate it and will be focused for, well, with aiming for a long focal length, but maybe the possibility to have also a short focal length parabola also there. The plan is to have the long pass beam and to have the 100 terawatt of Opel, but the main issue will be how we're going to deliver the beam there. So we see what we can do it. For the new target area, because new, the plan is to have all the beam there. So the plan is to have the 20 petawatt, the 6 long pass beam, the 100 terawatt Opel, plus the pump beams. So beam delivery will be a nightmare. In addition to the, obviously, the radio protection. For this, the new target area, the bunker will have a 2 meter of concrete wall, plus some additional shielding inside to stop the scattering going outside for the beam delivery, really. Now, that is a good story. What we need to do? Obviously, we need to develop the front end, because for 20 petawatt, we need to guarantee at least under 600 nanometer of bandwidth, stable for the front end with high contrast. And this is also related with which large crystal we can use for the 20 petawatt. There are only two options. One is LBO, and that is a DKDP. DKDP is more mature technology, looks like, but at the moment it's not easy to even find a large DKDP. And cost a fortune and delivery time is really long. LBO, the company wants to make a large LBO crystal, but there is no one at the moment that can deliver LBO crystal large enough for our need. So at the moment, we don't know yet which technology we're going to use, LBO or DKDP. And that will have different requirements for the front end. Synchronization, we have a problem because we're going to have 3 short passes, and obviously the user wants to have the short passes synchronized on target. So we know how we can synchronize it in the front end. And now we are looking how we can synchronize it at the end of the system. We have a collaboration with Southampton to work on Oracle Fiber, temporal fiber stabilization, and that is progressing well. And then we see how much we can synchronize. We need to develop the current disk amplifier. We have a first prototype, but we have additional work where to do it. Obviously, we still need to have large gratings with high dynamic damage threshold, a good efficiency. And that is always the issue. And the grating will be massive. And the mirror will be a problem because at the moment we are looking for something like a 720 millimeter beam that even bigger than the existing tap. So even bigger than 600 millimeter. So plus we want to deliver 9 long pass beam plus a 20 petawatt plus a 1 petawatt under vacuum plus the 100 terawatt all in one chamber. So beam delivery and beam transport will be a nightmare. In addition, that building is not a new building. We need to squeeze everything within the extension of the existing building. And the reason why we don't have a new building is simple, for budget. The new building will cost too much money. So the project is starting in July. It's not official, but is expected we start formally translate now. And for sure, in September, we're going to switch off Vulkan and we're going to dismantle everything. So with the plan for start to have the building, work on the building in January, March, something like this. And we have the building complete end of 2025. We will start to build everything again, beginning of 2026 or something like this. And start the commission in 2027. So the time scale is not long. It is quite compact consider that some of the optics got a delivery time of 1 or 2 years. At the same time, so in terms of conclusion, well, EPAC, we are starting to build the laser now. The pump laser is almost built in this other building. The front end is start to build it now, so on. The vacuum chamber compressor is close to be complete. And we also have the 20 petawatt, Vulcan 2020 approved and is starting with Vulcan closing down in September. And we have 3 months to remove everything. At the same time, we're going to keep Gemini, the Gemini facility operating. So because that it will be useful to support EPAC, but also because our user community want to have some laser. So Gemini, we're going to keep operational, and we're going to add the user, support the user during the downtime to do experiment on other facility around the world. Thank you for your attention.
Thank you very much. Do we have questions?
Hello. Daniele Margarone from Gianluca Computer, actually.
Yeah.
Hi. May I ask a question?
Yeah.
Yeah, go ahead.
Yeah, Marco, thanks. That's very challenging but exciting projects that you have been presenting. I have a question regarding the kilojoule or 10 kilojoule class, nanosecond class beam. 2 questions, actually. First is if you can, if I understand well, you can use the 10 kilojoule laser in parallel with the 20 petawatt short pulse beam. Okay, thanks.
Yeah.
And the second question is if you can work both in planar and in spherical geometries with the let's say kilojoule class beams.
Yes, essentially is that is the target area, and the plan is to have a beam delivery from one point, but then inside the target area there will be a different possible beam delivery to the extraction chamber, and that will be depending on what the user will ask. So it will be from both sides, or could be front or whatever. Experience for target area west, we know that the user can ask everything. So we see what we can do it, but will be not fixed geometry.
Okay, thank you.
Any other questions? So just to clarify, so here you talk about 6 long pulses that can be delivered to both experimental areas. That includes this up to 10 kilojoule, right?
Yes.
Okay. And so what are the advantage of having this 6 pulse? I didn't fully follow the...
Well, we want to have capability for fusion-oriented experiment. And we know that the community asks for 10 kilojoule at least. So the only way we have to deliver 10 kilojoule in a long pulse is to have 6 beam.
Okay.
As a comparison,
I got it now.
Yeah,
okay.
Orion has got a 12 beam to deliver 10 kilojoule. So we're already pushing what we can do it.
And the 100 terawatt that you mentioned here is also a long pulse, but Vopel is 30 joules, 30 femtoseconds, so it's a very different type of laser, what you mentioned here.
Yeah, Vopel is a fully OPCPA system, yes.
But that's really really nice to see this multi-beam with hybrid between many different type of lasers that will be available together in the same experimental area. Do we have other questions? Then let's thank Marco again for this very interesting presentation. And now we can switch to the second talk. So the second talk will be given by Daniele Garon from ELI Beamlines, and he will talk about high peak, high average power laser facility at ELI.
Hello, everybody. Can you see my screen?
Yeah, we see the screen, the pointer, and we hear you well.
Very good, thank you. So first of all, I'd like to thank the organizer, actually Gianluca, who invited me to deliver this talk, and it happened for me to be here at Queen's these days. So I'm good. I'm very happy that I can present from his laptop since mine is not working at the moment. Okay, I will. I'm trying to move. Doesn't work. Just a second. Okay, so actually, initially, I will give you an overview, and I will introduce the ELI Extreme Light Infrastructure, which actually is a consortium now. It's called ELI-ERIC. And in the second part of the talk, I will focus mainly on one of the three ELI facilities, which is ELI Beamlines in the Czech Republic, giving you an overview of the cutting-edge technology we are offering to users, and especially focusing on the current user offer, not just future capabilities. I am using this slide here not to remind you that Gerard Mourou and Donna Strickland have won in 2018 the Nobel Prize for CPA, but I wanted here to stress that ELI in general has been enabled by a technological breakthrough, which is the invention of the CPA. And actually, I think now it's time for this cutting-edge technology to be offered to users, and hopefully one day also a scientific breakthrough will be reached thanks to the technology that here we offer at ELI Beamlines. And ideally, this will be an experiment with a PI, an external PI applying for beam time at ELI. So we welcome users to submit high-level scientific proposals. Here you can see in this picture, actually the reason why EU has invested some money into the construction of and now the operation of the ELI facilities. So in fact, Europe is a world leader in both development and operation of high peak power lasers. And actually, this is true also because there is a very solid, very robust user basis, which has been built around during the last 10 or 20 years around the Laser Lab Europe consortium. So what is ELI? In fact, this is a multi-site facility. There are 3 facilities in the Czech Republic, ELI Beamlines. I will be talking about this today. In Hungary, the ELI Atto-2 facility, and in Romania, the ELI Nuclear Physics. I have no time today to talk about the Hungarian and Romanian pillars, but I will be happy to take questions in the end of my talk, especially if you want me to comment on the complementarity of the science case and especially of the user offer technological complementarity of the 3 facilities. The ELI-ERIC stands for European Research Infrastructure Consortium. This has been established in 2021. It is an international organization, and this is based on member countries, not institutions, but directly is based on countries or governments, if you want. And as you can see here from the different flags, we have a number of countries already in the consortium. Of course, obviously, the host countries, Czech Republic and Hungary. You don't see here the Romanian flag, but you will see the Romanian flag in January next year. That is a good news. But also other countries like Italy and Lithuania, which are full members. And then also we have Germany and Bulgaria as observers, and hopefully soon we'll see more flags. This is some statistics where only the ELI ALPS and ELI Beamlines facilities have been included at the moment. So we have more than 600 staff members, most of them researchers and engineers, technicians. And you can see here from the number of countries, about 50 nationalities, that we are a truly international facility. We publish a user call, and you can find all the information at our user portal, the Eli Eric user portal, for open access. And we publish a call every 6 months. So we had just finished to evaluate the proposal from the second call, and we are in September this year, we will publish a next call. Here are some numbers, some figures about the regarding the second Eli user call. So we have published this call as a single point of access. So the three facilities together, ALPS, beamline, and NP. We offer the number of primary sources, our lasers, secondary sources, and end stations. And we received about 100 proposals from more than 20 countries. And actually, one important thing that I want to say that the proposals are evaluated by an external peer review committee or different panels, and the evaluation is based purely on scientific excellence. And of course, since it is open access, it is not restricted to institutions coming from the member countries, but basically any PI from any institution in the world can apply and will be evaluated based on scientific excellence. So the distribution of countries in terms of PI, if we put together the first and the second call proposals, and again, here the numbers are based on Eli ALPS and beamlines only. MP is not included in this distribution. And you can see that there are, let's say, there is a quite healthy distribution with a lot of proposals also from countries which are not actually members of Eli Eric yet, like the UK, US, and others. But of course, there is a strong participation also from member countries, Italy, Czech Republic, Hungary. Let me move to the second part of my talk that again is focused on Eli beamline facilities in the Czech Republic. So Eli beamline beamlines is known also as the high energy beam pillar of the extreme light infrastructure. And here the term high energy beam refers not only to the primary sources, not only to the lasers, but also to the secondary sources. I will talk about this in a second. It's again frozen. Okay, good. So what we did and what we do at Eli beamlines is to develop or co-develop high peak power femtosecond lasers and operate. Now we operate 3 of the 4 lasers that we host at Eli beamlines, and each of these lasers is unique in its own class as a combination of high energy in the single pulse and also high repetition rate. I will show you some parameters in a second. These high peak power lasers are used to explore the interaction of light with matter, with plasma at ultra high intensities. And in fact, here Eli beamlines has a dual mission. First of all, to offer this unique laser technology to users who want to perform pioneering research in plasma physics, high field physics, nuclear fusion, and so on. And this is one category of user. The second one actually is to offer secondary sources, X-ray particles with unique features, for example, the bunch duration, the dose rate, and so on, to users coming from different communities, material science, biology, medicine, and so on, that they want to explore multidisciplinary application. And actually, they don't need to be knowledgeable in lasers or in plasma. So this is, if you want, a challenge, and this is something in a certain sense new that we want to offer at beamlines. Here you can see the layout of the Eli beamline facilities. So 3 floors. We have 4 laser technologies in the ground floor: L1, L2, L3, L4. Not very original in naming. And these lasers can be distributed to any of the experimental halls or target areas which are located in the underground: E1, E2, E3, E4, E5. And in fact, we already provide the L1 laser, which is a kilohertz multi-terawatt class laser, to the experimental hall 1 dedicated to AMO science, material science, and biomolecular application. I will talk about this. We have also commissioned the L3 petawatt class. It's not yet working at 30 joule, 30 femtosecond, but in the order of 10, 12 joules on target, 30 femtosecond. So this has been commissioned in 3 different areas: the plasma physics area, and then the ion acceleration area that we call LPHYS, and also very recently, we have performed the basic commissioning of the ELBA electron acceleration beamline in the E5 hall. We have also, and this is offered, actually, L3 is offered to users in the ion acceleration area. It was offered within call 2, and it will be offered for the next call 3, in the electron acceleration area. In the L4 laser is not yet commissioned at 10 petawatt level. Actually, the energy has been demonstrated, but we are working on the commissioning of the compressor. And but we already offer the laser in its uncompressed fashion, so nanosecond kilojoule class laser into the plasma physics platform. So here actually you can already combine this laser with a short pulse laser or a secondary source driven by the short pulse laser in the plasma physics area. It is already online. And the next year also we plan to commission our high energy X-ray sources, both the Betatron beamline which is here in the experimental hall 2 and can be driven either with the L3 or with the L2 laser. I will talk about the L2 laser in one of my slides. This is a development laser. It's a 100 terawatt class 50 hertz laser, which is not yet completed, but we want to complete it early next or in spring next year. And then last but not least, the LPHYS beamline, which is a laser undulator radiation beamline that also we plan to commission next year with both L3 and L2 laser. So as I said, actually all the laser can be delivered to any of the experimental hall, but of course we do it step by step. Also regarding the footprint of the facility, this is not really a very compact facility. It's 110 meters, the footprint on this side here. And you can see here a picture. Actually, it doesn't show up properly, but you can see half of the L4 compressor with the gratings, the 4 gratings, and the L4 compressor is the only compressor which is located in the experimental halls on the 10th floor, like the experiments. All the other compressors are located in the 1st floor and then distributed over several tens of meters. And here it comes the first technological challenge. We have, in fact, this is an example of the L3 laser distributed up to the solid target in the ion acceleration area. In this case, we need to transport a compressed beam in vacuum over 80 meters. And in fact, there are 13 turning mirrors in the path. And what we need to do is to preserve the quality of the beam in terms, for instance, of pointing stability. You can see here, this is a measurement on target of the pointing stability of the laser after 80 meters of beam path. And it showed an excellent stability, 1.3 micrometers RMS. And this is due to the stability of the building. And of course, it is due also, or it comes out of the very accurate engineering for the beam transport and optomechanics. Here you can see different steps of commissioning for the L3 laser. So initially, about 2 years ago, we wanted to see the beam quality on target after these 80 meters of beam transport without using any deformable mirror. Here, the intensity with 10 joules on target was not so bad, 10 to 21 watt per square centimeter, but you can see here a lot of energy outside the focal spot in the far field. Then adding one deformable mirror before the compressor, so still in the laser floor, we have improved clearly the intensity on target by a factor of 3. And in fact, considering that we are going to implement another deformable mirror in the target chamber, and we are going to ramp up the laser from 10 joules to 30 joules, actually a value of intensity of 10 to 22 watt per square centimeters should be at reach. Also, it's not just question of energy in the focal spot or stability. Also, we need to preserve the pulse duration, so bandwidth, the compressibility of the laser. And here, actually, you can, or maybe you cannot see the overlap between the, in blue, you should see the measurement of the pulse duration in the laser bay, and in red on target after 80 meters of beam transport. And they are perfectly overlapping. So we are in the level of 27 femtosecond pulse duration. Here, a few pictures of the free lasers and the free target areas that we already offer to users. We have offered them, some of them, L1 laser, which has a name, in fact, Allegra, into the E1 experimental hall for XUV generation and application have been offered already in call 1 and call 2. And then the other two lasers, L3 and L4 atom laser, uncompressed, as I said, nanosecond, offered within call 2 in the E4 hall for ion acceleration, AMI beamline, and E3, the plasma physics platform for different experiments in the field of high energy density physics. These are the features of the free laser we already offer to the users. So the L1 laser is an OPCPA system. It's based on ytterbium YAG thin discs, and it is fully diode pump. Most of the lasers that we offer at Eli beamlines are diode pump lasers. The target design is 100 millijoules. Currently, we can deliver on target 55 millijoules in 15 femtoseconds. So more than 3 terawatt peak power at 1 kilohertz, a very good contrast, also because this OPCPA system is based on picosecond pumping. Then the L3 HAPOS laser is a CPA system. It's a titanium sapphire laser, again, diode pumped. It's a petawatt, 30 joule, 30 femtosecond, currently delivering 13 joules on target, or 12 joules actually on target, 27 femtosecond. So let's say on the level of half a petawatt, and currently working at 3.3 hertz, but the design is to work at 10 hertz. So we'll be able to work at 10 hertz at some point in 1 or 2 years from now. The L4 atom laser is a, let's say, CPA system, also based partially on OPCPA technologies. And this is a not diode pump, it's a flash lamp pumping system, is a neodymium glass laser. It can deliver, or the target design is to deliver on target 1.5 kilojoules in 150 femtoseconds. So it's a long pulse, kilojoule class 10 petawatt laser. Currently, in the second harmonics, we deliver about half a kilojoule, a little bit less actually, in like the uncompressed pulse, so from 2 to 10 nanoseconds, with possibility to play with the pulse duration and also with the temporal shape, with a 0 or something like 150 picosecond resolution. The beauty of this laser is that it can shoot every minute. Actually, at the moment, we are using every 2 or 3 minutes, but design parameter is one shot per minute, which is of definite interest, especially for the community working in the field of inertial confinement fusion. So now I will go a little bit more in detail, not too much, per each of the experimental areas that I have flashed earlier. So the E1 experimental hall is a kilohertz area where we produce kilohertz X-ray sources, and we deliver these sources in different end stations for application. So the first one is the high harmonic or the gas harmonic source. Here we can deliver XUV photons in the range between 5 and 120 nanometers. And actually then we can isolate the single pulse and transport this beam into an end station. We call it MEC, which is a station for AMO science, but also coherent diffractive imaging. And we have a second X-ray source. We call it PXS. And in this case, we can deliver characteristic X-rays. In this, at the moment, we run with a tape target, so 8 kV. And this is not coherent, but it is spatially coherent, but also a Bremsstrahlung radiation from 3 to 30 kV. And these X-rays are used in an end station. We call it T-REX for X-ray diffraction and spectroscopy. Also, we have a number of commercial laser, again, 10 millijoule kilohertz femtosecond class laser driving optical stations. For instance, here for time resolved spectroscopy, ellipsometry, and transit current technique. But also we have a satellite laboratory where we perform ultra-fast optical spectroscopy using other commercial lasers. For instance, femtosecond stimulated Raman scattering is one of the stations which is mostly used. Here, the commonality between all these stations is the pump probe setup. So in fact, we believe that we can deliver or you can set up pump probe experiments with photons ranging from the mid-infrared up to the hard X-rays, and then with the resolution that down to femtosecond and time delays from femtosecond to millisecond, actually. We also use the L1 kilohertz laser focused down to few micrometers to reach relativistic intensities, so beyond 510 to the 18 watt per square centimeters. And this actually has been used, first of all, to produce or to accelerate electrons, like using the laser Wakefield electron acceleration scheme. And we call this station alpha station. And in fact, you can see here, thanks to the quality of the L1 laser, we can reach about 50 MeV electrons, quasi-monoenergetic and collimated using 55 millijoules on target. So we offer this station with a dual aim. First of all, as a platform for relativistic interaction at kilohertz, and this system can work at kilohertz. And second, also we offer the electron beam either for source development or for irradiation of samples. We receive some proposals on in vitro and in vivo sample irradiation, and also others on damaging test of electronics. Here you can see a beamline, the ion beamline, ion acceleration beamline driven by the LPHYS' petawatt class 10 Hertz class laser. In this case, we run the laser at 1 Hertz because the bottleneck at the moment is more the target refreshing system, target delivery system for a solid target. The laser is focused also tightly down to 2 micrometers, so we can reach intensities well beyond 10 to 21 watt per square centimeters, ion energy up to 40 MeV at the moment with 10 joules on target. Here the goal is again dual. First of all, at the moment we are offering the platform or the beamline as a platform for ion acceleration, so source development or tertiary sources, for example, neutron in picture catcher scheme. But then the other aim is to offer the ion beam with the good high quality in terms of energy spread and angular divergence to users coming from other communities. And for this, we have the so-called ELIMAT beamline that we will be commissioning in August this year. Here you can see on the bottom a series of shots, consecutive shots, either in single shot or in rep rate. This was at the early stage commissioning stages. And you can see there is a good shot-to-shot stability. In the center of the slide, you can see the progression towards higher proton energies that was naturally coming when we improved the laser contrast, nanosecond AC contrast from 10 to the minus 9 to 10 to the minus 11. This is the intensity contrast. Also, it's not enough to provide the high repetition rate laser or provide high repetition secondary sources to users, but we need also to provide diagnostics and targetry that can work at high repetition rate, so 1 to 10 Hertz for the petawatt class lasers. And this is what we try to do, first of all, to measure the laser characteristic on target, on shot, also X-ray, of course, particle beam features and plasma imaging spectroscopy. And at the same time, to be able to transfer data, so data transfer, but which is not enough, but also to analyze data, so data processing at 1 or 10 Hertz. Here you can see another beamline driven by the LPHYS' petawatt class laser. This is the ELBA electron accelerator, which aims at providing a platform for users who want to use a petawatt class laser for electron acceleration at up to 10 Hertz. And at the same time, again, a dual aim, also in this case, to enable electron photon collision using intrinsically synchronized laser. Actually, here we split the LPHYS' laser in 2 beams, and this will be a nice platform for the community working in the QED field. And actually, here I have a nice plot that I have stolen to Gianluca in the past, which shows the probability of electron pair creation using lasers with different intensity on target and electron with different energies. We would be here several GeV and beyond 10 to 21 watt per square centimeter. So we are in a nice spot, let's say, beyond the current state-of-the-art capabilities. And at the same time, considering the high repetition rate, 10 Hertz capability of the laser, this will be definitely a nice feature to have high statistics and robust results. Here you can see different type of platform. I have introduced this earlier, the plasma physics platform, where in principle we can deliver, and we aim at delivering all the petawatt class and also the kilojoule nanosecond uncompressed beam into one flexible modular experimental chamber. In this case, what we want to do is to provide a platform for user coming from the high energy density physics field, including inertial confinement fusion and shock physics. The beauty here is to have not only to have different lasers with unique capabilities, but also to be able to do these experiments at relatively high repetition rate. So 1 shot per minute with a kilojoule class laser. And this laser also, as I mentioned before, can be controlled in time with temporal shaping with 100 picosecond resolution, but also spectrally. So we can offer both the narrow band and the broadband option, which was mentioned before by Marco Galimberti in his talk. And we also want to provide a set of diagnostics and targetry, for instance, for laser plasma instabilities, shock physics, including BISAR, SOP, X-ray diagnostics, and in terms of targetry, not only solid, but also gas, multi-layer and foam target, for example, tape, and others. I did not mention earlier that in general for the solid target delivery system we are not offering yet, but we are working on cryogenics and liquid target, which I think is a must when you have a 10 hertz or even a few hertz petawatt class laser, to provide some robust solution to use this laser with solid target at a higher repetition rate, which is a challenge at the moment. Okay, this slide shows you why the plasma physics platform is interesting for those groups working in the field of fusion-related research. As I said, 1 shot per minute is a nice capability. I'm not going to read each line here, just to say that this platform is interesting, of course, for the physics studies, but also for technology studies. For instance, to mitigate and to study issues related to debris shielding, EMP, repetition rate, targetry, and also laser studies. As I mentioned before, the different how to switch from a broadband to a narrow band operation, so on. Okay, I did not mention the high energy yet, the high energy X-ray beamline. So the first one, we call it LPHYS, is a laser undulator radiation. And in fact, this is a first stage towards a free electron laser driven by optical lasers, by laser wake field acceleration. Initially, we want to demonstrate a compact approach to produce XUV pulses that we want to offer to users coming from the field, from the biomolecular imaging field, for instance. And actually, we are part also of the Eupraxia consortium, which is a larger network that you probably know in Europe. And Eli beamlines is one of the candidates for future implementation of this approach. And this beamline will be driven by the last laser that I did not describe earlier, which is the L2 dual laser. This is a 100 terawatt class OPCPA system working at 50 hertz. So high repetition rate, which is important for an average flux of the X-ray sources that we want to produce out of that.
Sorry to interrupt. You have 2 minutes.
Yes, I'm done. I'm the last slide. Thank you. And yes, and the picosecond contrast is very high intrinsically. And yeah, this is the last beamline we want to I did not mention yet. So it's the Betatron, but also Compton X-ray source that again can run with the L3 and with the L2 laser, so 10 hertz or even 50 hertz. So expected parameters are several tens of kV for the Betatron source and a few MeV for the Compton source. Potentially, if you synchronize the L3 and the L2 laser, we aim to commission this beamline next year. Let me remind you that for the PhD students, the Eli Summer School is going to be organized in the very end of August, so there is still time to register. And also to all of you, if you are interested in receiving more information about Eli beamlines, Eli in general, please join the Eli mailing list. You can use the QR code over here. And I guess that was my last slide. Thank you very much.
Thank you very much. Do we have questions? Yes, Christophe? Sorry, I got it. Do you have questions? So you presented a lot of different operating systems in terms of laser, in terms of experimental areas. In terms of where you are, from what I got, you got some ions up to 10 MeV or maybe more, and you got electrons into situations, the hyperparate and on the petawatt, you got hundreds of MeV. Is that right?
Yes, well, yes. Actually, what you saw, the shot-to-shot fluctuation on the ion beam, that was a initial stage of very beginning of the commission when the contrast was not good, so it was on the level of 15 MeV. But now with a better contrast, we are on the level of 40 MeV for the protons.
Okay.
And this is what we are offering at the moment. It's quite stable as well. And we projected energies are up to 100 MeV when we let's say increase the intensity or the energy on target. We are working with 10 joules only, so it's 400 terawatt on target. And in case of electron acceleration, it was again, these are very fresh results. It was the very first commissioning. Again, we work with about 8 joules on target. In this case, we were trying also to test the configuration with the splitting that I've shown to have the collision. And yeah, it was the energy in this very first commissioning was in the order of 600, 700 MeV. But this is just what we call technical commissioning. Actually, we have opened last Friday, if I'm not wrong, a call for the advanced commissioning of the electron accelerators, and which is called, we call it the user-assisted commissioning. So this is open to all the users. So everybody who is interested can apply for that. So the goal in the first stage of the electron acceleration will be to have a few GeV, let's say 1, 2 GeV with a counter-propagating beam, 10 to 21 watt per square centimeter to be offered to the community, for instance, work in the QED field or Compton scattering and so on, inverse Compton scattering.
Okay. And so this is like time scale of 1 or 2 years, since it's the coming call of the user-assisted commissioning.
No, it's not time scale of 1 to 2 years. So the call is now for the user-assisted commissioning, and we will perform the experiment in September, actually, this year. And in fact, then in September, based on the results, we are quite confident because the technical commissioning was okay. We want to offer the beamline for open access. So the experiments, open access experiment for the electron acceleration platform will be done starting from spring 2024 next year.
Okay, great. Do we have other questions? So let's thank the speaker again. And now we will switch to the third talk from Dr. Oshbota from Corels, who will talk about the observation of nonlinear Compton scattering in laser electron collisions. In principle, you should be able to share your screen.
Okay. Thank you for the introduction. Thank you also for the invitation and for the opportunity to present these results here. So today I will talk about the observation of nonlinear Compton scattering in laser electron collisions performed at the Center for Relativistic Science in Korea, South Korea. So this has been a big effort and many people have been involved, and these experiments, the preparations started already a few years ago. So I'll give an introduction about the facility and about the topic. Then I will discuss how we measure the beam briefly, and then the properties of these beams, and finish with some conclusions and future work that we might do. So As you know, there are lots of petawatt facilities nowadays worldwide, and one of them it's now in South Korea, in the city of Gwangju, which is actually in the southeast part of South Korea. So there is a university here, Gwangju Institute of Science and Technology, and inside this university campus, there is an IBS centers. IBS is a network of centers in South Korea, and this center is called the Center for Relativistic Laser Science. And for several years now, this has hosted petawatt laser facilities, which initially operated at 1 petawatt, then it was upgraded at 1.5, and then already since a long time it's operating at 4 petawatts. And recently, 2 years ago, it managed to achieve 10 to 3 watts per square centimeter intensity. So there are also some links here, but I don't know, this cannot be accessed now. So because we have such high intensity, we can actually use part of the beam to do acceleration and part of the beam to do collisions and to start exploring some more interesting physics that occurs at these intensities. So as I said, this is a bigger effort, and we also have some external collaborators that helped us with modeling, and several teams from this institute have been involved in the studies and in the research related to this topic. So just a very brief overview. So there are 3 major processes, let's say, of particle production in strong field QED that we are looking at. So it's quantum scattering, the nonlinear Brightwheeler, and the Trident pair production. But for our work here, we are focusing on nonlinear quantum scattering, and basically everybody in this field is trying to achieve as high as possible the quantum nonlinearity parameter. So one way to achieve this nonlinearity parameter is to use a counter-propagating electron beam with a very high relativistic factor, very high gamma factor, which then can shift the upwards the electric field in the reference frame of the electron. So basically, it's a shortcut to achieving electric field strengths close to the Schwinger limit, the limit which allows the pair production from vacuum. So this also achieving a high quantum nonlinearity parameters allow us to study Brightwheeler, but most likely first it will allow us to observe some quantum effects in the nonlinear quantum scattering collisions. And basically our interest is in this topic because it can reveal insights on radiation reaction on the photons energies that are produced, and it can also be useful to produce very bright and tunable and high energy photon beams. So there are, in terms of the background, there are, let's say, two major approaches to strong field QED. So one would be when we calculate the rates in a static field. So this is also called the locally constant field approximation or constant cross field rate. And usually this is implemented, the most common model implemented in PIC codes. So on the left side there is some PIC simulations that I did with this, and then the other approach, which works better for a naught smaller than 1. It's the plane wave model, in which basically photons are modeled as plane wave in the rate, and basically what we're doing in strong field QED, we're trying to explore and understand a bit what we can study about these models and how we can study. And in the case of these two models, we cannot really distinguish in the present experiments the differences between them, because these differences occur at very low energies. I wouldn't necessarily say low energies, but low, let's say, compared to the average energies. But what they have in common is these long tails that extends well beyond the linear quantum scattering limit. So it's an energy tail that Instead of having a Compton scattering limit at 100-150 MeV, this tail can extend to, in the nonlinear Compton scattering case, to up to 1 GeV. Okay, so there are lots of experiments. Initially, these experiments have been done in a low Waynaud regime and low energy regime, and depending on the regime that you're working, you are dealing with linear or nonlinear Thomson scattering, and then again linear or nonlinear Compton scattering. And for our case, for this work, we use electron beams that go up to 3.5 GeV. 3 to 4 GeV actually. We can get a PK naught of 14, and we can reach this quantum nonlinearity parameter up to 0.5. So far, this is the highest reached in such experiments, but most likely future work that will go beyond this regime will happen at accelerator facilities where the electron energy is much higher. So experiments such as LPHYS'23 FACET will also try to explore this regime of interaction. Now, for our particular experiment, this is the general setup. We actually split. We pick up part of the laser, the petawatt laser beam. So maybe you see my mouse. So this is the red one, the main 4 petawatt laser beam. And we pick up a part of it through a Holt mirror, and then we direct it through a very short off-axis parabola to the collision point. And the main beam accelerates the electrons. And after the electrons exit the gas cell, a few centimeters away, after already the beam has diverged some time, we are producing these collisions. And this collision is happening off axis because we wanted to ensure that we don't have some background from stray electrons that can be emitted from the during more complex trajectories of the electrons in wave field acceleration. So this is just a brief overview of the scattering beam and the main beam, the focal spots. We are with the scattering beam, we have around 2 to 3 microns, and 4 times 10 to 20 watts per square centimeter, while for the main beam, in order to accelerate the electrons up to GeV energies, we are using a much higher beam waist and lower intensity. So around 40 to 50 microns and around 3 times 10 to 19 watts per square centimeter. So just to also show to the rest, so this is how the inside of our facility looks. We are actually using a 12-meter long focusing for this experiment for the electrons, which poses additional challenge. And inside the target chamber, we are sending through multiple mirrors this scattering beam in order to compensate for the 24-meter delays between the two. Of course, we are correcting both beams with deformable mirrors in order to ensure a good quality focal spot. So for the wave field acceleration part, I think many people are familiar with it, and there is, especially in the last few years, there's been enormous progress in this area, both in terms of applications like FEL lasers, but also operations at very high frequencies, as you've recently heard in the previous talk, which is quite nice results to produce tens of MeVs of electrons at kilohertz frequencies. For our experiments, we are working because there are two major processes that limit the acceleration of the electrons to high energies. One of them being the pump depletion, and the other one it's dephasing. We have to compensate for this and to work in a bit lower density regime. So we work around 5 to 8 times 10 to 17 per cube centimeters, and between 3 to 5 centimeters length of the acceleration medium. So we are doing this in gas cells in which we have 97% helium and 3% neon in order to work with ionization injection. So we can get some good quality beams, although repeatability still remains an issue. But actually, in many of the shots we were able to obtain both good divergence, narrow energy spread, and this simplifies part of the analysis for the Comte scattering experiments. Besides this, we also had to implement synchronization. So this is also a major challenge for such experiments because you have a very large jittering between the beams at the focus, even though the divergence is, even though the pointing of the laser beam is small, it's still 12 meters focal length, and the entire beam transport has around 50 meters. So anyway, we implemented both spatial and spectral interferometry in order to observe the synchronization between the beams at long time scales and at short time scale. Longs meaning hundreds of femtoseconds, and short a few femtoseconds. And we were able to monitor this online, so shot to shot, to obtain the temporal delay between the two laser beams, and then compensate for the electrons. Okay, so for the measurement of photon beams during these experiments, in the upper left side is the setup. Outside of the vacuum chamber, we are using a beam profiling crystal, a scintillator, and after that we are using a pixelated detector, which works as a electromagnetic calorimeter in order to diagnose properties of the beam, of the gamma beams, of the background, and so forth. So here on the left side, I'm just showing the photos of these detectors, and then a brief overview of some GN simulation and of the response of the pixelated detector for 100 MeV photons and for 10 MeV photons. So the pixel size is 2 millimeters, and this gives us actually quite a lot of, it's 1 millimeter and gives us quite a lot of VSAT. We also use different pixel sizes, and it seems this is a very adequate specification for what we need, the one that we're using right now. Okay, just first a confirmation of the signal I'm showing here. So in the upper part, I'm showing the signal on the left side on the electromagnetic calorimeter when we have a collision, and on the bottom side when we don't have collisions. These here are not really the best shots that we have, but in any case, the signatures are very clear, and the background in further campaigns we reduce it much less, so we can have hundreds of thousands times more peak signal and also a peak integrated signal in cases where we have collisions and when we don't. And additionally, the signatures are also very clear. We also have signatures with multiple backgrounds or multiple other beams and so on. So we confirm it, and here I'm showing the signatures of other processes. For example, in the first part, in the first column, you see a signal. Below, it's measured in experiment, and above it is from this spectrum in PIC simulations. On the central column, it's an example of Bremsstrahlung radiation. This can also be produced in experiments if you want to. So you can just add a foil and then you'll see these kind of signatures. And also of Betatron radiation, which in case of GeV electron beams that were close to 10 to 18 can produce quite high critical energy that ends up penetrating significantly through such a calorimeter. And that's, well, a signature of the high energy. We analyze this more, but I'm not going to focus on this today. So for the properties of these bright gamma beams, first I will I'll just briefly overview the analysis for the detection. We are using two methods. In one of the methods, we are iteratively extracting the spectrum without any assumptions. So this is called SIRT, so simultaneously iterative reconstruction method. We adapted this. This was used in this usually it's used in tomography, but it was also used for Compton spectrometer in some of the experiments that the Nebraska group did before. So I adapted this for the PER spectrometer. And the other method, which was maybe more standard for such experiment, is one that approximates this the synchrotron-like function from that appears or that describes the spectrum of the nonlinear content scattering gamma beams. So I'm showing an example here of measurements and reconstruction for a low energy photon beam and for a high energy photon beam using the two methods, and also the reconstructed line out on the detector. So the error, it's basically the error here, it is within the manufacturing errors of these detectors. So I think the agreement is very good, but we looked further into this. The critical energies for these two shots, it's around 50 and around 100 MeV. And we observed in principle three categories of shots. Those where collisions are barely happening, so most likely there is low intensity at which the collisions are occurring, and they have low shots. They have low energy. The gamma beams have low energy, around 50 MeV. Then those at which the critical energy described in this spectrum, it's at around 80, 90, up to 100 MeV. And then high energy shots, maybe in this case is the electron energy extends to 3 point something GeV, and the intensity it's also very high. And then this in these cases it can extend beyond 150 MeV critical energy. These results were also compared and calibrated with PIC and analytical simulations. So analytical simulations have been based on actually numerical on a numerical integration. So you can check more about this model here. And maybe one of the things that we discover in these experiments is that the two-dimensional structure of the focal spot, in fact, the three-dimensional, because we also tried to compensate for additional focusing effects along the focusing direction. So this really impacts a lot the average energy of the gamma beams, average or critical, if you want energy, if you want to describe it by that. And anyway, considering this detection, also the detection limit and this multiple experimental analysis and simulations, we can get maximum energies. In this shot that I'm showing here, it's up to close to 500 MeV. So basically it would mean, in a physical interpretation, one could say that an electron in its reference frame absorbs 300 laser photons, and then it emits one gamma photon in the laboratory frame, carrying a very, very big energy. But this high energy extends even to up to 1 GeV. And for the angular distribution, so as I said, we can also measure that, but we did not see a significant asymmetry. In fact, we were expecting a high asymmetry based on previous works, but because of the collision geometry and all of the parameters at the collision point that we have, the electron beam, it's in fact that experience a very low effective or average A naught. So although we have a collision with a very peak A naught, the effective A naught it's small. So then these photon beams will inherit the divergence of the initial electrons, so not the not a divergence significantly modified by the intensity effects at the collision point. Although this effect it's present, still these photon beams have a high number of gamma rays. So basically, it means that if we would be able to collide these two beams if we would be able to collide the laser beam with an electron beam that has much less divergence, then the brightness of these beams would be even higher and even more impressive. And maybe we could also see some divergence effects. Okay, so we could also extract the photon numbers from these experiments, because we can just calibrate our optical detection system and we know the properties of the emissions. We also know from simulation the expected energy deposited into such scintillators for different energies. So basically, then from the total count, we can get an approximate number of gamma ray photons that are produced, and which is on the order of 10 to 7, and in some cases reaching or surpassing 10 to 8. But we analyzed these things. However, we wanted to make sure that we can be confident and we can fully simulate the detector response, because this would have to also include various backgrounds and so on. So on the left side, we are simulating, let's say, the upper limit that we have on the experiment when we had a critical energy above 150 MeV and more than 10 to 8 photons. And this is the signal on the detector. This is below the signal on in our simulation. The varying intensity of the pixel is as I said before, the manufacturing defects or different emission rate for each pixel because of the scintillator crystal or because of the reflection inside these pixel cells and so on. And maybe what is more important, it's the also the lower limit of what we can see in these experiments. So in this case, again, we had something like this in experiments, and in this case, we couldn't exactly extract the critical energy, but we could just approximate it for this lower limit, and then do these GN4 simulations, and also includes all of the parameters of the imaging system. For example, the noise of the camera, the horizontal noise that we have in these CMOSs, and then take into account the efficiency of the optical detection setup, and basically get an image very, very similar to what we had on the detector. And besides this, of course, there is also the noise that can happen in these experiments, because the laser electron collisions and generally Wakefield-based collisions are not facilities built for only this purpose. They're facilities built for many applications. So we had to do some shielding, and we also checked the configurations of the shielding with Fluka. So what we found out is that of course, there is always some background. So if it is, if you want to do a very sensitive measurement where we can measure 10 photons with 1 MeV energy, that would be challenging. But if we are measuring high energy that goes above 10 MeV, and we are measuring high photon numbers, then these contributions basically are insignificant. In terms of numbers, for example, we have less than 10 to 5, so on the order of 10 to minus 6 times less particles. 10 to minus 6 times the initial number of electrons would be the total number of particles above 10 MeV. So maybe we'd have, I don't know, 100 particles or less than 100 particles could be the background at tens of MeV. So yeah, this would confirm that we don't have any problems with the background. So based on the properties that we measure, the expected beam size that we see also from the PIC simulations, the divergence and the photon numbers, we get a very high brilliance, 10 to 20, around 10 to 23. So this is some of the brightest beams in the MEV regime, and as far as I know, the brightest in the above 10 MeV. And it's especially interesting because at much higher energies, close to 100 MeV, these are maybe sixth order of magnitude brighter than what has been produced with other sources such as Bremsstrahlung. Okay, so now to finish with the conclusion. So these experiments are important because they can also give us in the future insight into some processes in astrophysics, such as the electric field or the magnetic fields around magnetars that go beyond the Schwinger limit. The gamma beams can also have applications in nuclear and photonuclear physics. Especially the high energy going above 100 MeV can also of the gamma beams can also allow pion or muon production, but would also be interesting in photon collisions, such as, for example, these recent proposals on the gamma factory, and would also be important in medicine, such as flash radiotherapy. And for further work, for example, we already did some experiments in which we try to improve even more our detection by using photonuclear activation and simultaneously using photonuclear activation with multiple detectors. So we can activate we can activate a target, and then with HPG detector, we can measure the activation. And we also use the pair spectrometer based on electron-positron pair production to measure GeV electron photons, but we're still analyzing the results. Okay, so in conclusion, we demonstrated this nonlinear inverse Compton scattering in the highly nonlinear regime. We clearly can confirm the signal. We can distinguish various sources and backgrounds. These beams have more than 100 MeV. These gamma beams have more than 100 MeV photon energies. They are ultra bright. And currently, our results are consistent with what we get from multiple simulations. Okay, thank you. I think I finished in time.
Thank you very much. Do we have questions? Yes, go ahead, Christoph.
Yes, yeah, very exciting talk. Of course, it's that you have seen nonlinear Compton scattering at these extreme intensities. This is fantastic. I just wanted to ask a bit about the theory. I'm not sure how much you can answer here. You have shown in the beginning some of a bit older works where nonlinear Compton scattering has been calculated within the local constant field approximation, also plane wave approximation. And then you were later comparing with quantum peak codes. And so basically, just that I'm not lost, when you're comparing your results with these codes, what are the approximations that have been used in these codes? Are these local constant field approximation plane wave results that just to see how much this is state-of-the-art theory you have been using?
So thank you for the question. Mm-hmm. Yeah, it is the LCFA, so the locally constant field approximation in particle.
And can you say if this is valid in this parameter regime you have?
So it fits with our results so far, but we are looking, let's say, at an intermediate energy range for this spectrum. So we are basically looking for the slope from maybe 10 MeV to 700 MeV, and the slope seems to be consistent with what we observe. So we try to actually input.
Okay, so you basically that's. Yeah, of course, there are also theoretical ways, right? I mean, first, of course, there are suggestions, how to, include these terms into the code.
Right.
That would be a possibility. But of course, there are also parameters that basically, theoretical parameters that can tell you if this is valid. But of course, it's a good sign that your experimental results are sort of fitting to this. But of course, this is something you want to prove, right? You want to prove that you have experimentally detected it, right? So that's why I thought it would be a good way to compare your results with those state-of-the-art models, or of course you use these theoretical parameters also to show that these approximations are valid, right? I mean, this is the way I would do it, but of course I see your point that that these things fit closely together. So it sounds like you are in a regime when this is valid, and the other approximations you. So plane wave, basically in these codes you've been using, plane wave rates have been used, right? Not, I mean, I guess you have, I would guess that you have very strong focusing to get these extreme intensities, right? So,
right.
And sometimes there's an order of magnitude difference in the results when you include the pulse shapes, and if you don't, that's why I would be interested.
So you are absolutely correct. So in principle, we cannot do some more straightforward estimation because the A0, we have to deal with an A0 distribution, whatever we are doing. We cannot fix, let's say, a value of A0, and we have some nice work, but it's not yet, it's not going to go out on various effects that lead to a departure from this let's say simple, not simple, but a more parametric based estimations.
Okay.
So it is the whole the ANA distribution that it's based on the focal field at the focus, the jittering between the electron and the laser beam, the timing, so all of this. In fact, I initially did, because even from some of these models, you can you can extract, let's say, an average energy based on analytical calculation. So I did that, and then our results didn't agree. And then I realized that, okay, we have it 3 or 4 times less than what the analytical estimation would show, because we cannot simply take into account in that analytical estimation all of these effects.
Okay. Thanks a lot for your answer.
Yeah, thank you.
Gianluca?
Yeah, thanks. Hi, Colin, and thanks for the talk. It's very, very interesting results. Regarding the divergence of the gamma ray beam that you were showing,
yes.
So we did actually quite a lot of work to extract A0 from these kind of distributions, and the thing is that using simply the formula that you're quoting is a little bit like zeroth order, because you're not, for instance, you're not taking into account that the electron loses energy as it traverses the laser field. So gamma, for instance, in that formula is not constant, and electrons emit many times in the laser field because it's, I don't know, 12, 13 cycles or whatever. So if you want, we can talk about it offline, but we do now have a more detailed model to look at the distribution, the angular distribution, the number distribution of the photons, and extract effective A0s from that, taking into account, energy losses and many other effects. That formula there is good as a zeroth order, estimate, but it doesn't take into account a lot of things, as you know. I'm sure you know. But anyway, if you want, we can talk about it offline.
Yeah, this is yeah, for sure. This is just an indication what I'm putting here, and it's the next step to look at this.
And the second thing, quickly, if you look at the gamma ray spectrometer results, the cesium, the long calorimeter results. The question I have for you is, what would be the energy uncertainty, the energy resolution that you have? Because I think in the graphs you only show the yield error bars, but not the, this kind of graphs. What would be the actual uncertainty in energy? Because with these, the convolutions, it tends to be quite big.
Well, I try to calculate based on some analytic estimations, like on the penetration depths and so on for the calorimeter. So what I get around 20%, 10 to 20%, something like this. Because it's not. I mean, I have to think how to physically define this error, right? From these things, so it's not so straightforward. But maybe with the displacement, for example, of the pixels, this is one of the approach that I'm thinking. So this is why we went with the very narrow pixel sizes, because in fact we observed that had a better characterization with very small pixel size.
Yeah. Okay. Right. Thanks.
And of course, it would depend on the energy that you're looking at. So, and 20% of the energy, let's say.
Yeah. Okay. Thanks.
Thank you. We can take the next question from Sevim.
Michael, thanks for the talk. My question about the gamma ray spectrum.
Yes.
We can stay on this figure. So I want to know why the size of the error bars increase as you go up the energy.
So in this case, it just depends on the way that we did the extraction. So I use logarithmic binning for this, and there is a reasoning for that. So in case that you are applying this kind of method, let's say to the content edges, you can do it linearly. But in case you are applying to a calorimeter, the penetration, it's not linear, but it's logarithmic in the electron energy. So because of that, I use the logarithmic energy bins, which in turn would give a higher uncertainty at the high energy.
Okay. But would you say that so TFM is the constant field limit that you're using in the analytical formula? And or
Sorry?
TFM is just the I want to know what the TFM stands for. Is that the constant field limit as the trial function, or just the random function you're using for the fit?
Okay, so TFM and SRT are methods of analysis. They are experimental. So that's why I'm showing the slide. So the TFM, it's just a trial function extraction, but with a function that is supposed to characterize well the synchrotron emission in the low energy and in the high energy. So that's why it has exponential tail for high energy and power law for the lower energy. So the LCFA, it's basically both in the QED and the analytical model, it's included.
Okay, I apologize. Last question. So to the high energy tail, it seems that there's some divergence between data and the models. Would you agree with that? And could you comment on it, please?
So indeed, you see a divergence, but it's below the detection limit. So we try to define also a detection limit for this method of extraction, and I think that's the reason why the divergence is there. So this is also characterization over three orders of magnitude, right? In terms of the photon number, and 2 orders of magnitude in terms of the energy range. So in my opinion, these methods have to be combined at least to two methods of diagnostic. And I don't mean like we did here, two extraction methods from the same, but two or three different devices. So what we are trying to do now to have simultaneous nuclear activation, pair production, and calorimetry at the same time for a single shot. Otherwise, it is within what we can say experimentally.
Thank you. Appreciate it.
Okay.
Thank you. We can take the last question from Swotong.
Thank you. Very fantastic work. My question is about the angular divergence, angular distribution of the photon beam.
Yes.
Yes, this figure. For me, the angular distribution is the azimuthal symmetry, right?
Okay, yeah.
So, but you use a linearly polarized laser background, right?
So, sorry, I use
the laser pulse is linearly polarized.
Yes.
So I assume for example, if the laser is polarized in X direction, then I think the photon beam, the angular distribution of the photon beam should be broader in X direction.
Correct. In principle, theoretically, yeah.
But you figure is azimuthal symmetry, so I don't understand.
The problem is the difference between some idealized model and the complex effects that you have during the experiment. It is it's true, it is linearly polarized in principle, but it's also at an angle. It also doesn't hit exactly in the center the electron beam. So some of electrons will experience more A naught, some of electrons will experience less A naught. There are also, I do not know if there is a petawatt system that doesn't have various spatio-temporal couplings at the focal spot. There is the fact that we are using an off-axis parabola, so then the field structure will very, very fast move away from an idealized the field or intensity focusing. So all these elements combine to ultimately give something that is not extremely is not what we expected. And in addition to this, there are also the contributions of the electron beam, right? For example, you can have electron beams that are more or less symmetric. So some of them are not symmetric. So then you cannot distinguish which are the contributions that on the asymmetry that come from electron beam and which are the contributions that come from collision. So it's a lot.
Okay,
it seems simple in the beginning, and the experiment in Nebraska was very nice to show these things, but it also happened at a much lower gamma factor, which allowed more divergence if these things are happening, and the laser beam was also much higher, so that's why they observe that well. And then there is still another problem that could occur, which is some betatron background at this level, because the betatron is quite strong here. It gets to critical energies well above 100 MeV, so even it can penetrate a bit of your detectors. So if you are doing a profiler measurement, you have to be very careful on how to split these contributions.
Okay,
so I'm not sure if this answers.
Okay, thanks for your reply.
Yeah.
Okay, so I think we can conclude the session here. So thank you again, Kalin, and all the speakers. And we resume with the next section at 10 a.m. Thank you, everyone.
Thanks a lot. See you in 10 minutes.